Trajectory-based operations, or TBO, is an air traffic management concept that enhances strategic planning of aircraft flows to reduce capacity to demand imbalances in the National Airspace System, or NAS, and provides tools to air traffic management personnel and controllers to help expedite aircraft movement. Through improved strategic planning and management of traffic flows, TBO helps reduce reactive decision-making and use of static restrictions and increase the use of existing PBN procedures. The aircraft trajectory is a cornerstone of TBO. Defined in 4 dimensions: latitude, longitude, altitude, and time, the trajectory represents a common reference for where an aircraft is expected to be and when that is defined prior to departure, updated in response to emerging conditions and operator inputs, and shared between stakeholders and systems. Improved data sharing and information exchange is another cornerstone of TBO. Facilitated by the FAA's Integrated and Consolidated Information Management System, collaboration between the FAA and operators is continuous and includes both new and more frequently updated content. For example, based on their business goals, operators provide and update individual flight status and routing preferences. Based on demand and operating conditions, the FAA provides flight-specific information about release times from departure runways and expected times of arrival to the runways at destination airports. TBO also expands electronic coordination between facilities and capitalizes on expanded digital communications between traffic management personnel, controllers, and pilots operating equipped aircraft. During non-peak times, aircraft in the TBO environment enter the NAS in essentially the same manner as in the pre-TBO environment. There is less need for complex automation and controller decision support. Airspace users file their flight plans and provide aircraft status information to FAA automation. Traffic management personnel use this information to anticipate aircraft movement from origin to destination and use their predicted trajectories to proactively address potential capacity to demand imbalances throughout the NAS. In the pre-TBO environment, traffic management personnel and controllers have limited decision support to help them manage aircraft flows in the NAS. Limited in both functionality, what types of problems it can help with, and availability, where in the NAS controllers can use it effectively. Additionally, most of these decision support tools were designed to help manage local constraints and have not yet been integrated. As a result, they cannot adequately evaluate downstream constraints and cannot help with complex strategic or system-wide solutions. As demand increases in the pre-TBO environment, miles and trail, playbook routes, and other static restrictions are often needed to manage congestion. Such blanket restrictions are difficult to surgically apply to particular aircraft in the traffic flow. As a result, traffic flows may become over-constrained or under-constrained, potentially leading to lost throughput opportunities or a need for additional controller intervention such as vectoring or holding to achieve the proper spacing. Sustained periods of imbalance in airport capacity and demand levels may require activation of ground delay programs and, in severe cases, ground stops. In the TBO environment, traffic management personnel and controllers will have access to a suite of time-based management, or TBM, tools. Decision support with improved functionality and targeted availability throughout the NAS. This support can be customized to address site-specific operating conditions, integrated across different flow management functions, and used as needed to strategically manage aircraft movement throughout the NAS. A key cornerstone of the TBM concept is a network of meter fixes and arcs, which are strategically placed to manage constraint points in the NAS. This network focuses on improving the timeliness of aircraft reaching their arrival runways by simultaneously sequencing multiple traffic flows all the way back to their departure runways, and by applying applicable spacing through shared resources. TBO is focused on ensuring that aircraft are able to land on the arrival runway at their destinations in a timely manner and move through the NAS as the system is able to accommodate them. To help deliver aircraft to the terminal boundaries on time, we typically adapt each of the corner posts on or near the terminal radar approach control or TRACON boundary as an arrival meter fix or arc, represented as black arcs. Each meter fix, or arc, has its own schedule, a timed sequence of aircraft that are scheduled to fly through it that is based on estimated aircraft movement all the way to the arrival runway. Each meter arc is associated with a freeze horizon, represented as black dashed arcs. When an aircraft crosses one of the freeze horizons, the system estimates the time of aircraft arrival to the meter arc based on the flight plan routing and aircraft performance characteristics, determines the earliest time and position of the aircraft in the sequence of aircraft over the meter arc, and schedules the aircraft into metering timelines by accounting for the applicable spacing and determining any delays that may need to be absorbed by individual flights in the sequence. The sequence number and the timing of this aircraft in the metering schedule is now frozen, and only necessary changes may be applied by controllers and traffic management personnel as needed to address any unexpected developments. Aircraft outside of the freeze horizon are also known to the system, but their movement is still too uncertain for finalizing their schedules. Uncertain because of airborne winds and possible deviations from expected routing, and therefore uncertain in terms of the exact times of crossing constraint points. As a result, successful TBM requires management of aircraft movement upstream of freeze horizons in a manner that is harmonized and consistent across the participating facilities. To help deliver the right rate of aircraft to arrival metering freeze horizons, TBM relies on the following additional airborne metering capabilities. Adjacent Center Metering, or ACM, enables the system to receive aircraft position data from adjacent en route centers. With ACM, the system becomes aware of the aircraft before it enters the arrival center, which enables metering to start in the adjacent centers. By expanding the distance from destination over which aircraft are actively metered, compliance with schedules can improve. However, ACM lacks the ability to schedule flows inside the adjacent center's airspace, and only allows for TBM calculations and delays to be passed back to it. Coupled scheduling introduces the ability to incorporate additional freeze horizons and provides sequencing through additional constraint points prior to the meter fix. Similar to coupled scheduling, extended metering, or XM, is an advanced airborne metering capability that enables both delay passbacks to adjacent en route facilities and sequencing of upstream flows. This capability uses its own meter arc and freeze horizons that extend the distance from destination over which aircraft movement is managed. Adjacent center metering, coupled scheduling, and extended metering enable TBM of airborne aircraft. Departure scheduling and surface metering, on the other hand, support TBM of aircraft prior to takeoff. Departure scheduling capabilities help determine feasible departure release times for smooth integration of departing flights into already established traffic flows. The type of departure scheduling used for an aircraft is dependent on the types of constraints it will encounter en route to its destination. Departure scheduling into the arrival system facilitates integration of departures directly into an arrival traffic flow at its destination airport. En route departure capability, or EDC, facilitates integration of departures into en route flows. Available at all centers in the NAS, this capability does not consider potential constraints beyond the EDC meter arc. It simply determines a departure release time based on required miles in trail at the meter arc and the status of other aircraft in the same en route flow. Departure scheduling into XM facilitates integration of departures from airports between XM freeze horizons and associated meter arcs. This capability helps with scheduling departure release times based on the traffic congestion through the XM arcs on their route. In addition to decision support tools that perform complex calculations to estimate and manage aircraft movement, TBM also includes tools for electronic coordination of departure scheduling and information sharing between facilities. Some towers use Integrated Arrival Capability, or IDAC, to schedule aircraft directly into an overhead stream without the need for a call to request a release time. At airports where IDAC is not available, tower controllers continue to use phone calls to coordinate release times with en route controllers or traffic management units. Surface metering completes TBM prior to takeoff. It is part of a broader set of future surface management capabilities that use integrated information to more accurately predict surface events and conditions and more efficiently balance surface demand with capacity. Integrated information includes status updates provided by operators, runway configuration, and departure release times. Surface metering enables tower controllers to act on the improved predictions and schedules, resulting in smooth movement of aircraft on airport surfaces. Finally, another future capability, Terminal Sequencing and Spacing, or TSAS, will bring TBM to the terminal environment and complete the integration of TBM decision support tools across all phases of flight. This capability will be introduced at select busy TRACONs to help maintain metering schedules all the way to the arrival runway thresholds. TSAS will provide tools to TRACON controllers to help them maintain the runway-specific sequence and metering schedule. As long as an aircraft stays inside their slot marker, merging and sequencing will happen as scheduled through each key constraint point inside the TRACON. It is important to point out that, even after TBM capabilities are deployed and integrated, and quality of accuracy and information improves, some uncertainties will remain in the NAS. Airborne and surface winds, severe weather events, and other schedule disturbances will continue to present challenges and will sometimes cause unexpected delays. These types of disturbances are especially problematic when resulting delays need to be absorbed over a short distance to the next facility or the destination. In spite of the challenges, TBO will bring significant operational improvements to the NAS. TBM capabilities will provide integrated traffic flow management across functions and facilities and will be strategically implemented at select locations as needed to support traffic flows and operations across the NAS. TBM applies spacing only when needed to support sequencing and merging of aircraft, and alleviates the need for static restrictions. TBO will shift towards increased use of advanced PBN procedures in support of improved compliance to TBM schedules. In turn, improved compliance to TBM will alleviate the need for lateral maneuvers in support of sequencing and merging of aircraft through shared resources, and enable even higher increase in PBN utilization. Many of the activities performed by traffic management personnel, controllers, and pilots will be supported by automation and electronic communications. This increases timeliness and effectiveness of air traffic management. Controllers and traffic management personnel will remain responsible for safe separation of traffic and managing of uncertainties in the NAS. TBO will also facilitate seamless coordination between towers, TRACONs, and en route facilities. TBO will evolve through incremental improvements that build on each other over time and deliver increased predictability and efficiency of NAS operations.